Yeah, we know. And today is going to be a bit more theoretical. We're going to look into machine learning a bit. So we're going to take the start and the bulk of the lecture to explain a bit how machine learning works, what are the problems it solves, and so on and so forth. And then we'll see how we can implement some machine learning, neural network specifics on TensorFlow. So to start, we'll start with what is machine learning, and basically when you talk about in the general discussions in media, AI and machine learning are the same thing, but they are not. Right? There are a lot of AI systems that are actually not machine learning based. For example, you have tree search for solving chess. This is not machine learning. You basically are finding a certain measure and optimizing it by searching all possible solutions up to a depth of, I don't know, 8 moves if you're not really so good, 16 moves you're a world champion. So depends on what you want to spend. But this is an algorithm that solves a specific problem by looking for the best solution of the possible alternatives. Machine learning is something completely different. It makes predictions. It finds problems, it classifies things, but it does it not being programmed to do so. Right? So you don't put any intelligence from you as programmer into the model. You learn directly from the data that you collect. So, and there are some different flavors of machine learning. What we will do is supervised learning, which means you have a set of data and you have a set of labels that you want to connect with this data. For example, typical example is if you have images and you want to classify them. Let's say this is a dog, this is a cat, right? It's very simple. The main part of the image is the subject of the image, what class it is. This is supervised learning, but there are other sets part of other types of machine learning. For example, unsupervised learning. If you, for example, want to distinguish where one object ends and one other object begins, you don't need the labels, right? To do this, you can actually start doing it with unsupervised learning all over the place. You just need to understand where object and where object begins, or if you want to cluster data, that's another possibility you can do. Unsupervised learning is a bit more difficult to structure to find a way to make it work. But you will encounter it if you delve a bit more in machine learning. Besides this really tip of the iceberg that we'll do today, then there is reinforcement learning, which is usually a multi-step process of learning directly from the environment by interacting with the environment and giving reward or penalties for successful behavior or wrong behavior over a certain process. So with a delayed behavior. Now, won't go in that either, but it's something that is really important and coming up recently for many applications. So when it comes to supervised learning and deep learning in particular, most people think about neural networks, but that was not the case until 14 years ago, more or less. Before 2012, nobody was using neural networks, and everybody was using support vector machines with manual, for example, for image classification, with manually engineered feature extractors with filters that would then create a certain feature map and then support vector machine with kernels to actually fit the data in a certain way. So this was the state of the art until somebody came up with the idea to implement a certain type of convolutional neural network, which is called AlexNet. It's the first neural network that actually had a big success in image classification, and it beat the benchmark by, if I remember correctly, 30%, while the previous increment were like 1%, 0.5%, right? So it showed that there was an incredible potential in this. So what are neural networks? Well, neural networks are inspired, really inspired, and don't quote me on anything that I say in the next 5 minutes because I'm not a biologist, but inspired by biological neural network. That what do biological neural network do? Neurons in general collect stimuli from other neurons, from the axons of other neurons, and when the stimuli surpasses certain threshold voltage, they fire through the axon this voltage, and this stimulates electrochemical transmitters from the axon to other neurons, right? So basically, it's like a gatekeeper that when enough stimuli has arrived to the neuron, it will stimulate in the synapses where its own axis is connected. And this creates a process where information basically flows in a way that is defined by how strong are the synapses between one neuron and another, and creates pattern of thoughts. So what people thought is, can we replicate this? Can we actually create a mathematical system that does the same, more or less, with the simplification that comes into putting it in a computer on silicon? And they come up with this structure. The idea is that you have neurons that are collecting data from several source neurons, like they're connected, like this. And this neuron collects all three inputs. These are the inputs from the external. For example, this could be the three colors of a pixel, or the XYZ of a position of your robot, right? And then here you have some internal neuron that collects this information and decides that if this is greater than something, then I'll fire as well, okay? And I'll inform my output neurons of what I've learned. So, and they might have different weights. So they collect this information in different weights. Maybe this output increments the value of this neuron, but these other outputs decrements the value decrements the value of this neuron. And for the same input, this neuron reacts in a completely different way, right? It might be exactly the contrary. So how does it work in detail? And basically, let's simplify this a lot. Let's consider one single neuron that has three inputs. For example, RGB on a pixel, right? So what you do is you actually, inside the neuron, you have three weights. Let's also simplify the neuron is only one output. Usually it has multiple outputs, right? But in this case, it does only one. And what it does is it multiplies its own weights that it learned, times the input, and sums them all up. So it's a weighted sum of its input based on the weights that it has learned already. Plus, there is usually a bias, which basically moves up or down the threshold of what is a successful signal. When I say threshold, is because usually you have a nonlinear activation. I mean, usually, always you have a nonlinear activation. Usually, this nonlinear activation is the rectified unit, which is basically 0 for any input that is below 0, and it's the linear function x for anything that is greater than 0. So why do we need a nonlinear activation? Anybody can think about this? Does this work if I don't use activation?
Get more feature.
In which sense you think? It's around the right track, so you will get more features. But what does it mean mathematically? So if I have a neuron, right, I can do this operation. It gives me, if I try to learn with one neuron, gives me actually some important information. I cannot learn more than this with one single neuron. But what happens if I put another neuron on top and I try to learn the same again without any nonlinearity? So what happens if I have, let's put it this way, what happens if I have two-dimensional space vector x1, x2, and I have a linear operator A, okay, from R2 into R2. And now I combine this linear operator A with the linear operator B. So I do A times B. Can I write this as a single linear operator C? I can, right? So if I put two neural networks, these are linear operators. If I put two linear networks after another, I don't win anything because I can always rewrite the combination as one single neuron, right? The only thing that saves me from this is that I use an activation. If I use a nonlinear activation, this is no longer possible. So I basically am separating certain aspects that I want and I'm treating them linearly from certain aspects that I don't want, and I'm ignoring them. And then I apply a new linear operator that does the same. So I basically select and cut, and I can figure out, instead of dividing the space with the linear system, I basically divide the space, but then only take this part, and so on, right? So I can build shapes in my space that are not linear. If I have a different activation, the system will be different, of course, right? So what does this mean in detail? think again about the problem of a neuron. Let's say you have two inputs parameter, right? What is a single linear neuron without activation? Is basically drawing a line and deciding where is the threshold. So the line could be up here or down here. The neuron builds a direction. And then with the threshold, it decides what is good and what is bad. That's all it does, right? So if you have one single neuron, you have a linear model. And then basically you are deciding how to classify things one way or the other. Now, let's say that these are your data. This could be, for example, pressure and temperature in a sensor that you have. And this could be good events or bad events for what you want to accomplish with this sensor, right? So if you have a linear system, you can't really separate them because it's clear that this relationship is not linear, right? So what you want is enough nonlinearity to separate the good from the bad, or to classify if there are more than two classes. And you can do this by basically stacking neurons or using multiple parallel neurons and then summing them again with a nonlinear activation. There is a catch though, because if I give you enough parameter and I give you enough data, if I give you some data set and I give you enough parameter, you can always fit it. But what can happen is that, what this happens all the time. What can happen is that you end up with something like this. For example, here now I introduce a bit of noise in my data. So not every time, not necessarily every time that the temperature or the pressure are over a certain threshold, the event is good or bad. It can be some noise on the boundary. But nobody thinks really that this is a good model for what I'm doing, right? Because it's just you as at the first sight, you understand there is some noisy process here, and the fact that this point is here and this point is here is just random. So if you model it this way, you're going to actually fail more than if you model it this way for new events, not for the events that you train it on. This is going to improve, and you're going to fit them 100% if you have enough parameter. But once you get a new event, and we'll land somewhere here. I'm sorry, this is a bad example. Let's land somewhere here and said, yeah, this is a bad event. No, actually, it's more probable that it's a good event than it is a bad. Same goes for a new event that lands here. So this model will not outperform the original one just because it fits better your training data. And that tells you, for one thing, that when you train a neural network or any machine learning system, you have to be very careful how you select your training data and how you select your test and validation data, because they need to be uncorrelated, not just different. I'll give you an example. Many computer vision systems that we work with, for example, train on video, right? So you have camera, like a 3D camera with that, and then we want to train on this particular sound box, right? So what we do, we acquire this data with a 3D camera, we reconstruct the scene, then we recreate the model, okay? So then we have the label, because the label is the position and the model of the thing. Then we say, okay, now with the model and the orientation and the relative position of the camera to the object, what we can do is we can label each image and put the position in the label, right, of each image, because we know the relative distance. So what happens if I now take, let's say I have 1,000 images from this, and I take a random set of 800 images and say this is my training set, and a random set of 200 images, and this is my test set. Do you think there is a problem, or am I doing the right thing? Ideas? Who says that it's good? Who says it's bad? Okay. Why is it bad? What's going on here? I'm taking different images, right? There are different images in the training data from the one that are in the test data. Are they correlated? Taking a video, okay, with a camera. And let's say in 1 second I have 30 frames. On average, of these 30 frames, 25 will land in in the I didn't do calculation, but around 25 will land in the training data, 5 will land in the validation data. But then again, the difference between a validation frame and the frame before and after, it's not really big, is it? It's possibly some fraction of a millimeter, right? So yeah, I'm training in different images, but they are not uncorrelated from the validation data that I'm using, right? So it's an illusion, the validation. It's not a validation. To do a proper validation, what should you do? Who has ideas? What could we do to do a proper validation set for this problem?
Separate the pictures randomly and don't let the near pictures to the training data and the validation test.
So you say, I have my video, okay, and I separate it in a way that my validation frames, okay, are at a certain distance from my training frames, so to say. Right, I mean, this is one way. Basically, what you can do is really take a part of the video and set it as validation, take some buffer in between, and then take training data. It's not bad. This is basically taking 2 videos, right? But you're still correlated, because this box is still on this piece of wood and there's this object next to it, and it's this illumination of when I took the video, and so on and so forth. So there are a lot of factors more into what the correlation between the training data and the validation data is that will lead you to overfitting if you're not careful, right? So a good idea would be to take this box, put it in another room with other people, with other lights, and take a new video, maybe with another camera even, you know, so that you randomize as much as possible your things, and do this for training data, and then take a new place never seen, new lighting condition never seen, and so on, and do one set of validation data there, maybe another set of validation there somewhere in the garden, I don't know. So this will avoid you these kind of problems, because if you have this, then what happens is when you try to overfit, when you try to put too many parameters on it, then the system will tell you that you're overfitting, because your validation set will tell you you're not solving the problem. Because once you get out of your training data, it's not working anymore, right? But if your validation data comes from the same set, they will fit neatly, right? They will fit perfectly on your overfitted moment. Right. So what kind of neural networks do we have, and what we can apply to problems like this? The first and most simple architecture for neural networks is what we call a multi-layer perceptron. The perceptron is what we just saw as a neuron. It's basically collecting inputs, having an activation function, and transmitting when the activation function is over a certain threshold. Is actually used, this is as old as me probably, this is actually used, not as old as me, but nearly. This is actually still used everywhere. In many modern architecture, you find multi-layer perception that are either used as an output layer, for example. Very typical in a classifier. If you have an image classifier, you still use convolutional neural networks for the backbone, but at the end you flatten everything, and we'll see an example of this, and you use a dense layer, a multi-layer perceptron layer, to actually output the classes, right? But it's also used in particular places in other architecture with particular goals. For example, graph neural networks that are used to process the features of a particular node, and this is multi-layer perceptron, and it's used on all the nodes in the same way. Or when you process point clouds, a way to process point clouds is by basically associating with every point in 3D a set of features, and you process them with a shared multi-layer perceptron in most cases, right? So, and then there is some other clustering and manipulation, but at the end of it, it's still a multi-layer perceptron by default, right? So it's the simplest and most efficient one. Except it isn't in most problems when you use just that. For example, let's say we have an image, and we want to process this image so with all the pixels, as a multi-layer perceptron. How do we set up our architecture? Well, let's assume it's a grayscale. So every pixel is an input neuron. So you have basically to line them up. So you have like 4 rows of this, right? Each one is a neuron, and so on. And then you have another layer of neurons, and all of them are connected to all of the pixels, right? And so on. So what happens is that if I learn how to recognize a shape here, and now I'll move this shape over here, does it work? If I just seen in the training data the shapes in this left upper corner, and now I see in validation data a shape, the same shape, same color, same size, everything, but on the other corner, on the opposite corner, will it work? Right? I mean, these are the neurons that they get activated from this. These are this, and this, because I took these 4 neurons, I flattened them out. Okay, so now I have these connections that get activated. And this is the feature that recognize this guy, right? I learned these weights. That's the only weights I learned because I only saw the shape in that corner. If I activate these neurons that are somewhere down here, will this neuron be activated? No, why?
They have different weights.
Exactly. So these weights have nothing to do with these weights. So I don't have a chance to learn it if I don't see it. So if I'm using a multi-layer perceptron to learn from an image, I have to see the shape in every possible position, everywhere. Otherwise, it doesn't work, right? Moreover, it's very inefficient because it's not only a problem of data, because you need to have this data. Otherwise, you will not learn. But even if you have the data, you really have to learn every time new weights. So it will take an amount of time that is much higher than what you usually have with another architecture, right? What will happen with convolutional neural networks? Now, you remember we did convolutions before, in I think the last lecture and the lecture before. There's a filters, right? Are just matrices that you can move around the image. Now, if you have a convolutional neural network, this filter is not set up by yourself, like an edge filter, solid filter, and it's learned. So you don't design it; you actually learn it from the data. But what happens is that if the shape is moving, this filter will get the same input just from in a different place, and will activate the same layer in the output, and will associate this output to the position where it saw the image, because the neural network will take an imaging input, right? The filter will run through the whole image and generate another feature map. Not really an image, but it's a feature map, where if the shape is here, it's going to activate here that particular layer that recognizes that shape, right? And if I move the shape here, well, it's going to be activated here. So it is a lot more efficient, because with one filter, which is only 9 weights in this case, it will recognize that shape and it will be done. Once it has recognized it in one place, it can actually transfer it any place of the image. But it's not a solution for every problem. If you have a flat image, convolutional neural networks work fantastically. If you have a 3D space, it's not so easy, right? You can say, okay, you could bring it to 3D convolutions, but then you have to deal with what you call voxels, so 3D pixels. But what you see usually doesn't have that density. You see only surfaces, because you don't see behind the table, right? So what you see is an envelope of whatever is the word out there. You don't have to understand the hair between me and the table when you see. You just see the table. So your abstraction level and the camera inputs are not as dense as a cube full of solid pixels. So you cannot do a 3D convolution. So you have to find other ways to do it. And there is a lot of research in trying to find optimal ways to actually perceive 3D space using, efficient neural networks, right? But definitely not a convolutional neural network. The convolutional neural network doesn't understand that. It doesn't understand 3D or 3D convolutional networks because we don't have enough dense data and our sensors don't work that way. We don't feel everything from, with the camera from here to the object and beyond. It's not what we do, right? So, but still, it's one of the best tools you have if you want to do machine learning on vision. There are other neural networks architecture, just mentioning them so that you know what is out there. Recurrent neural networks, mainly not so much used nowadays, except for special things, and maybe in machine learning, in reinforcement learning, you'll find something when the system needs to have a memory. There's like an LSTM, which is long short term memory, in the input. But otherwise, it was more things before attention took over, right? What is attention? Attention is a process for neural networks to learn not only from data, but to learn which data is important. And it simplifies basically things like neural language processing, text analysis, basically, because it can, based on the learned patterns on the text, it can decide after this word what part of the input text should I look for. For example, if you're a chatbot dialogue like ChatGPT, or if you have a translation system, part of the output, the translation system is a great example because part of the output, for example, if we're going to translate to German from English, if you are at the end of the phrase, in German you have to put the verb. The verb in English is at the beginning. So the system must know that at that point it needs the verb, and therefore the attention must put it back at the beginning. If you were doing this with a recurrent neural network basically store a memory of the past tokens. Tokens are words or part of words or syllables and so on. So if you store a memory of the past token and translate in English to German, you are at the end, you must remember what was the verb. But that memory decays with distance. Long correlations like this are hard to catch for a recurrent neural network. With attention, it's very simple because it just needs to learn that it needs to look where the verb is. And therefore, it takes the whole sentence every time in input. It identifies where the verb is, and then it passes it as input to the next layer that does the semantic understanding, right? So this is the attention. There's two layers. The first one tells you what is important, and the second one decides what to do with it. Okay? And then there are other structures. I choose one because we worked with it recently. Graph neural networks are, for example, something that where you learn structures on top of graphs. So you let the graphs form itself, for example, and create a structure among nodes in a way that you couldn't do with any of the other things. What do you use this for? Well, for example, we used it to model relationship between tasks that are running on different cores, precedence relationships, and learn how you can extend this network or precedence relationship to create a what you call it a stable schedule, a predictable schedule on the course that you have available. So these are learning structures. Okay? But very interesting. We won't say anything about this stuff except what I just said. How do you train a neural network? The process is always the same, whether you're using attention, MLPs, or actually, even if you're using other machine learning systems, mostly is always this. So you process the input, right? You at the beginning, you have just random weights, whatever. You just randomize everything and you're done. Then you put the image in the input, let's say, and you want to classify at the end if it's a cat or it's a, okay, that's a bad example because I want to show you something. Let's say that you want to learn the age of the cat in the image, okay? So you have a linear scale from 0 to 20 years, and based on the picture, you learn, You predict how old the cat is. So first you show it the cat, and it puts a random number out there, something like 15. Well, you compare it to the label is actually 10. Cat is 10 years old, right? So what you do is you measure the error, it's 5 years. And then what you do is you correct the weights on the neural network so that instead of 15 is 14.5, right? It's just a fraction of the error that is connected to a certain learning rate that you want to fine tune for your problem. And it pushes the neural network to predict something more similar to the label. And you do this over and over and over for hundreds of times or millions of times until it predicts the right age, right? So basically, and here we say, let's take that the prediction is the age of the, well, the age of the cat cannot be negative, but let's suppose that the prediction is the age of the cat, okay? And if you fix the input, the image input, basically the only thing that the prediction depends on is the weight value, right? I simplified for one weight. There's always tons of weight that you have, but you have partial derivatives, you all done analysis, so you know how that works. So let's focus on one weight, and let's focus on that age of the cat. How does my age varies when I vary the weight? And I fix the image, I don't change the image. That's what I'm interested in, because once I know that, I can take the gradient and I can basically go down the gradient towards my original label, right? So if I call the error epsilon, this error, I take the partial derivative of the output to the weight, and then I adjust for learning rate, minus, of course, because I want to go back to the origin, to the good label, not progress in the error, right? And that's my delta W. I adjust this weight by delta W, and I'm down. Right? Make sense? So this is the basic way to train neural network. Of course, that little parameter is a bit of a boring, bothersome parameter, because you can tune it, yes, but maybe you start with a parameter lambda that is good, right? Because you think, okay, I'm very far, I want to do big jumps. But when you're near, then you keep jumping and missing the target every time, so you're going wild. So it would be nice if you could adapt this and have a system that actually adapt the lambda as you start learning better and better. And there are many optimizers out there now that do this job for you, so you don't have to care about it unless you're very interested in machine learning algorithms. Otherwise, you just use them. You probably heard the name Adam, right? So this is one of them, Adagrad and so on. So usually this problem is solved for you if you're just using machine learning as a tool. If you're interested in doing research on that, that's a different story. So let's go to the examples and see how we actually can train in TensorFlow and neural network. So this is, I think, everybody that has gone through machine learning has seen NIST. It's a classification of letters of numbers. So what we're trying to do here is to take an image, which is 28 by 28, and it has an handwritten number. That could be a 0, 1, 2, 3, 4, 5 until 9, right? And the idea is that we build this neural network to classify this number, this handwritten number, and put it into an output that is one of 10 output neurons. And depending on which output neurons has the highest value, we decide that that's the number that we have predicted, right? So this is also called one-hot encoding. So if you have, for example, this is our vector, not really great vector, but whatever. So your vector, the value is 3. This value would be 0, 0 for 1, 0 for 2, 1 for 3, 0 for 4, and so on, until 9. Is this clear? What this means? This is called one-hot encoding. And for our output, you're going to use one-hot encoding. So we'll always have 10 neurons as output, and you will never get a clean prediction like this, that 0, 0, 0, 1, 0, 0, 0. You get 0.1, 0.05, and so on and so forth. And there will be a 0.8 maybe here, and then you say, okay, it's a 3, right? So let's see how we start from the bottom. This is an interesting stuff here. So this is our model for our neural network. Let's look into it a bit more. So this is how you define this one simplest way to define a model in TensorFlow, and I'm only showing you the simplest one. If you're more interested in digging a bit more, you find a way to control better the gradients, to define more complex model and so on. This is a sequential model. It's built with Keras, and basically what it does is that it takes your input and it runs them through these layers. So the first one of this list is the first layer that will get your input and spit out some output. This output will be given to the next layer that will give some output that will be given to the next layer, and so on, until we get to the last one, which, as you see, is dense layer with 10 outputs, because it needs to predict our integer, right? 0 to 9. So this is a multi-layer perceptron. One layer or multi-layer perceptron. And you specify this layer as dense, and you give the number of neurons in the output. You don't care about the input. The input is going to be understood from the previous layer. Whatever you put it in the input is going to be used as input. So this is the same as another dense layer, is the hidden layer in between. It's bigger, 128 units instead of 10, and it has an activation, our rectified unit. Yeah, that's how you specify it. And before I do that, this is a very simple neural network, right? One hidden layer, actually not even. This is the input layer. One input layer, one output layer. That's all. Sorry. This is the hidden layer, of course, because I read this data. I create 128 values, and then I output it in 10. Okay, so there is an hidden layer, sorry. Okay, this is the first dense layer are these synapses. The second dense layer are these synapses. Don't count the neuron, count the synapses. So the flatten at the beginning is necessary because I have a two-dimensional system. I have 28 by 28 pixels, and to feed it into a dense layer, I need to flatten them out. What I do, I just tell it what the input shape is, and I use this flatten layer, and that's all I need to do. So it's very simple to design, and you can play around and add layers, add neurons, remove neurons, whatever you want, and see if it improves performance, improve accuracy, trains faster. You can play around with this. So how do I actually move it to compile and run it? Compilation is quite simple. I need to tell it a few things. For example, what's the optimizer that I want to use, right? We use Adam. And pass it a starting learning rate. And then I want to say, what should I measure? Because so far we didn't speak about it, right? When I have a quadratic problem, like for example, I'm measuring age, I could say, for the cat, right? I could say, well, my error is the quadratic distance of the age, the label from the age that I predicted. That's simple. In this case, we use something a bit different, which is cross entropy, right? So if you're interested about it, you can read about it, but let's put it this way. It measures the difference in categories, right? It measures if you have one naught and one naught on one side and as a label, and you have a prediction that is all over the place, it will tell you that, that particular value in the vector, that it should be 1. It's not 1, so how much is the difference is a particular function. And for the 0, is another function, and it sums them up together, and it tells you what's your error. And you minimize this, you minimize the loss. So in many cases, for simple problems, you can use one of the losses that are already given for from Keras. And usually what it means is that you either use quadratic error for anything that outputs a continuous value, or you use cross entropy for anything that outputs categories. These are the two choices, unless you do something more complex. And then matrix is not really important. We use it to output our categorical accuracy. Leave alone the sparse. The sparse really separates you. Well, I mean, if you give in the label as numbers, you can use sparse categorical accuracy. If you give the labels as one-not labels, so with all the whole vector, you can use categorical accuracy. It's just a technicality. But they measure exactly the same thing. Measure the amounts of prediction, correct prediction, over the amounts of events. So they do, okay? So you give this and you compile it. And then there's a little program called summary, a little fun method called summary that will actually tell you a lot of things about the model. We'll see it, right? Which layers are there, how many parameters, and so on. So let's leave alone the display callback. We'll come to it later. This is the fastest way to train a model. You just use model fit. You pass it the data. Let's see what it is. Say how many epochs you want to run it, right? You pass it the validation data. And let's ignore the callbacks for now. That's it. And that will run your neural network training. So you have to do it. So for the data, you have to do a bit more work. But in this case, we actually are cheating because we're using TensorFlow datasets, which includes a lot of datasets that you can just use it without downloading. It will be downloaded for you when you start the program. So it's very convenient. And in this case in particular, we use TFDS load. We say we want to use MIST, split, train, and test, and so on and so forth. You can do all this thing, what they do. But basically, it gives you an array that where you have already your training data, your test data with all the labels and so on. So it does, but you still have to do some work. Because when you download this data, you will download images with 0 to 155. And what you want to do whenever you have an image, for sure, bring it down to 0, 1. So do this. Put it in float instead of integer, divide it by 255, so you get a standard range. Sometimes you will also want to go a bit more into the details, and instead of doing just 0 to 255 down to 0 to 1, you might want to take the maximum and the minimum of your data set and kind of normalize depending on the range you are using, not depending on the range you could use. Because it might be that all your images are very dark, so you want to expand them to use the all possible spectrum. Also, if you do this in the pre-processing of the data, and you also do it when you apply the neural network in real time, it will be more robust to change the lighting. So if you are able to filter your input and answer your input before you feed it into the neural network, you will save the neural network from learning about all the different illuminations that you might use, right? So the fact that we are doing machine learning doesn't mean that we cannot use also smart ways to simplify the lives of our neural networks, because that means that we can train them faster and have better accuracy. So remember always to consider whatever you can do to help the neural network along. And this is one of the things. So normalize the image. Once you have done that, right, there's a few more things that you might want to do. I mean, caching, shuffling, setting the batch size, and prefetch, basically optimizing the way you treat your data set. This is something that you can find. It's a standard way to treat your data set. This is copied over from the TensorFlow documentation. You can tune it and you can test with it what works better. as always, this is performance. It's really just performance. So what you do is you set it up, you measure, you find if you have a problem, and if you have a problem, you go back and change it. If you don't have a problem, just ignore it, right? Performance optimization, again, I think I said this before. To do performance optimization, you measure your problems, find the biggest 5 not bottlenecks, and you solve the easiest one. You don't solve the one that is causing you more problems. You solve the easiest one. Then you measure again, because they might have been gone. You might have solved the others as well, or they might have been have become actually more difficult to solve or have more impact. Then you have to roll back the other change that you did, right? So measure, solve the easiest one, measure again, and so on. So if this doesn't cause you any problem, don't even implement it. If you have a performance problem, then you have to dig into caching and batching. I mean, batching you have to do always, but prefetching and so on. Right? So same goes for the test data, and then we're done. So now we have our train data, our test data, and we have our info with the labels. So now we can test it, but before you can test it, I mean, we'll get the loss, we'll get the categorical accuracy if we run it like this, but we won't get to see the images, and we won't get to see the classification on examples, right? Another thing that you learn if you do data science is not just about to know the metrics. It's about also learning how your system behaves and what data does cause it problem and why is it learning it. So you, by looking at the data, looking what data learns, what data doesn't learn, you can get a lot more insight than just looking at the loss function, right? So what I did here is create a callback function that you can then use in the callbacks. Now, if you're doing this the proper way, you should use something like TensorBoard, which is a web interface where you can see all the graphs and all the outputs, and you can plug output as you will images inside, for example, and see the image directly there and scroll through them and so on. But for this simple case, I just created a callback that I can call in my feed, and this callback basically goes through a bit of validation data and plots them, and also tells me if they were wrong or right. So what I did in this case is I created a matplotlib plot, and I did 2 things. I first went through just 10 of them, showing both goods and bad, whatever they are. And for the rest of it, like I have one batch of 128, so I went through the rest of the batch, and I checked if the predicted class is the same as the label. If it is not, then I plot it, right? And so that I have always 10 examples of something that works or not, but I see for that batch all the examples that don't work, so that I can see where it's getting stuck, right? And yeah, if I get to fill the plot, I never was able to fill it. If I get to fill the plot, I just break. Right? I have 50 errors in a batch of 128, I'm done. I think I have enough information to see. The plot function is always the same. It's basically creating a subplot, putting the image inside as grayscale, and then give it a title that tells me what was the true label and what was the predicted label, right? And that's basically it. And this is just setting up the image and the iter and so on. So we run it with callbacks, and now we can actually run it for the first time and see what's going on. Right. So first of all, we have 100,000 parameters. 128 neurons in the hidden layer generate 100,000 parameters. For me, at least the first time I did this was kind of a surprise, because I never thought about it before. The synapses are a lot more than the neurons. If every neuron in the input layer and every neuron in the hidden layer connect, you have 28 times 28 times 128. That's a lot of synapses. That's why you have all these parameters. So it's about 5 milliseconds per step. our loss went from 0.6 after the first epoch, so went through all the images. And how many images do we have? We have 469 steps. How many images did you train on? You don't have to do the calculation, just tell me what the calculation is.
Times the batch size.
Exactly. So every step basically has 128 images. So you do this, you have more or less like 50,000 images, 60,000 images, right? So we trained 60,000 images per epoch. We got the first time around cross entropy loss of 0.63. Doesn't tell you much, but what it tells you something is the sparse categorical accuracy. So on the training data, it did 82%, 83% of predictions correctly on the training data. On the validation data, 0.94. So 94% correct. How's that possible? What's going on? First of all, does this surprise you? That is going better on the validation data, on the training data? Think about it. When is the training data being measured? While it trains, right? First, the neural network is garbage. Put a new image, get the output. The output is garbage. There's 1 chance out of 10 to get the right one because it's random, right? So that accumulates here. That counts. Get the second, it's probably also garbage, and so on and so forth. Until I get like, I don't know, 10,000 images, maybe I start learning something, and then it starts to be correlated, right? But I still have this this 10% accuracy from the first 10,000 images, right? That I have to subtract from the final result. So that's why the training accuracy is lower. The validation accuracy is measured at the end. I already trained for a whole epoch before I actually went and validated this, right? So that's why 94%. But then I do the same in the training, and you see it's higher, 95%. And at the end, now it's similar, it's 95.97. So if we go on, it actually surpasses the validation accuracy. So the validation accuracy between, it's still learning, right? Between here and here, it went from 97.15% to 97.51. So it jumped to 0.35% in accuracy. While the training accuracy, it jumped a whole percent point to 98.39%, right? And yeah, so it works pretty well, I would say. I mean, out of 100 logits, it gets 97%, 97 correctly. It gets 3 not correctly. Shall we look into what doesn't get corrected? Right. I mean, let's be fair. It does a good job on this, right? 2, 0, 4, 8, 7, so on. Actually, let's see the first one, the one that it started with. It should be this. All right. It actually did a good job on this one. Except this one, that was a 3, and it predicted a 5. But you can understand why. It's actually pretty difficult, right? So on this below, these are the wrong one. This is the line of the one that it found in the batch that were wrong. It's only 5. And that was the first epoch, right? So 9 predicted 0, but it's not really that off, right? Okay, this is off. This, frankly, I agree. It's a 0, right? Again, 3 with 5, it's hard to distinguish them. And 7 and 1, I mean, this is a 1 to me. Okay, I think he's right here. It's the label that's wrong. All right, let's look at the last epoch prediction. So look at that. Our 1 is still there. It's convinced, and I mean it's right. But the rest, it did a good job with everything, even if with the original 3 to 5 problem, right? So he learned pretty well. Still has this problem, still has more problems because 97%. I mean, we didn't see all these examples because there's 30,000 images. We just tested it on 128. But we saw one of the problems, it's reasonable. Okay. So let's look into neural network of a different sort, CNNs. Find the everything. All right, so CNN, this is exactly the same program. The only thing that I changed is the network design, right? And there it is. Now, I wanted to show you something a bit more complex. What I did is I parameterized my network. So what I did is I decided I want to parameterize both the number of channels of my filters, and I want to parameterize the number of layers of my filters, of my network. So what I do is I multiply my structure 8 times n, 16 times n, 32 times n. These are the output layers, the output channels, sorry, of each filter for each of these convolutions. So the first convolution takes as input my image, 28 times 28 times 1, because I have a grayscale, and it outputs 28 times 28 times 8 times n. So if n is equal to 1, 8 channels. What does that mean? It means that for every pixel in the input image, it can tune 8 different pixels to understand what's going on at that pixel. For example, it can tune 8 different edges. 1, 2, 3, 4. Right? It can detect these 8 different edges with just this layer. Right? If I increment this, it might be able to detect 16 layers. If I put this 2n, it might be able to detect the difference between this and this, you know, black white on one side or black white on the other side. This system would not be able to, because there would be 16 different filters. So this one might decide either to detect independently of where the color lies, or to detect only this, and one, two. Oh no, I'm sorry. These are actually 4. So it detects all of the edges. If I have 16, I can detect also other kind of edges. All right. So, but we just sorry for the mess. I wasn't counting. So with just these 4 directions, I can detect 8 edges for each direction with black white or white black. All right. This is something that this filter is able to do with 8. The more you increase this number, the more complexity it can detect with a single stage. The other thing that I did with a little trick is enhance my network by stapling layer after layer on top of my filters with new filter of the same kind. So this is really exactly the same as before, just that the input stage is already been upgraded to 8 channels. So it will take the same input and the same output as always. And I'm telling it to do padding same, which means that I don't lose pixel every time that I do one convolution, right? Because otherwise it will lose the edge pixel all the time. So can you explain to me what I did here and why this thing works? Why can I create more layers with this star bracket for something in range n? Basic Python that we learned. You remember how this works? This is a list comprehension, right? The one in brackets. So it's creating a list of these layers for as many as m. But why the star? What's going on? And who? What happens if I put a star in front of the list? What happens if I do this? Basically remove the brackets, Remember arcs, star arcs? That's exactly the same thing, right? So if I do reference basically a list with a star, I basically explicitly put all the elements of the list inside this list where I am right now. So in this way, I can construct this loop inside the list and then put all the elements in the bigger list that is creating my sequential model. And in this way, I don't have to, mess around with other structure. I can directly use the sequential model as it is. So I'm doing this 3 times. And now I have basically, so with M1 and M0, I have the basic system with just one layer. And then you have this max polling 2x2. Now, max polling 2x2 is quite an interesting thing. For each of these 8 layers, max polling will start at the corner, take the value here, the value here, the value here, the value here, will select the bigger one, and you put it in the output here. And then we'll take this one, take the value here, 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 take the biggest one, might be this one, we'll put it in this output, right? And so on and so forth. But it could be different for the next channel, right? This max polling does it by channel. Right? So now what I have is half the pixels. In X, half the pixels in Y. This is given by this proportion 2x2. So if I take 3x3, it will take 3x3 regions to take the max polling. Right? This way, I reduce my dimension from 28 by 28 times 8 to 14 by 14 times 8. Because I'm just max polling, right? So now what I do is I input it in the same convolution 2D, but I increase the number of channels. Why do I do that? First of all, I don't need to do it, but it is convenient to do it. How many parameters do I have? How many parameters am I learning? The filter is 9 parameters. Okay? How many channels do I have? 8. So 9 times 8. How many times do I apply this filter then? On all the pixels, right? And these pixels are based on the size of the image, 28 by 28. So here I'm reducing to 14 by 14. Now I'm learning the same number of parameters, but I am applying them 1/4 of the time. So I can use more GPU, let's say here, to actually increase my channels and still have a complexity that is similar to the one above. I'm increasing by a factor 2, so I have still half of the computation that I had before. So that's why it makes sense to actually increase the feature counts when you go up in the pyramid and start max polling. The other reason is that these might be, these features here might be edges, right? As we saw before. But these features here might be actually something more complex. And you might have more features that you care about, the more you get abstract. We know that this is quite standard. If you're learning convolutional neural networks on data, you basically always find these edges. And even the biological neural networks. There is an experiment that is quite controversial nowadays, but they did on cats by measuring their neurons, and they found out that they actually fire when something that they saw at a particular inclination. So even biological neural networks learn this way. It's universal. But once you go up in the hierarchy to more abstract features, this one have a lot more variety. Right? At the highest level in the computer vision system, you recognize part of a face, for example. If you're learning on humans, you recognize an eye or a nose. And there is so much variety in that. I mean, think about all the parts of the face you can recognize, all the different features of texture, of textile, and so on, right? So these could be thousands and thousands of features. But at the beginning, you still have those 16.8 features or 32 features that give you all the possible information. So that's why you keep increasing this number, because you want to make space for more abstract features, right? So beside this, it's just more of the same. I'm just passing this through, putting an activation every time, ReLU, right? So I buy a lot of nonlinearity here with this model. Putting activation, passing it to max polling, convolution again, activation, max polling, convolution again, activation of polys. At the end, I have a 7x7 map, okay? So a lot smaller than the original image, 1/4, with 32 channels, or 32 times n. And these I flatten and I put into a dense layer, right? As I said before, we need at the end a dense layer because I want to recognize these 10 categories. And I want to learn if I have these abstract features here and this abstract feature there, it means it's a 4. This is what this is doing. It's looking at positional information and feature activation. So if I have an edge here like this, and an edge here like this, and an edge here like this, that's a 4, right? That's what it's learned. But it does it through this dance. Okay? Is it clear how this is structured? All right, let's see it in action. All right, 21,000 parameters. Do you remember the count of the other one? What, 100,000? Not 10,000, 100,000, 130, something like that. So this old structure here is actually a lot smaller than the MLP. Why is that? What was the MLP doing? It was connecting the hidden layer to every pixel. That's a lot of synapses again. The filter is not doing that. It's collecting nine neurons to 9 pixels below, and then it's moving, right? So that's a lot less parameters. But nevertheless, takes a bit more time. The other one was processed at 5 milliseconds. This one is processed in 9 milliseconds per step. So we're not, ignoring the complexity of applying this filter to every pixel 5 times instead of just 1. We have to pay for this in computing time. But the memory, which is sometimes actually more important than the computing time, because if the model is too big, you cannot fit it into your GPU, then your computing time goes through the roof. Because you have to unload your model, load the part, do the computation, unload that part, do the next part, and do the computation, and so on. Forget about it, it doesn't work. So if the model doesn't fit in your GPU memory, you're done with it. But if the computing time is a 2-per, it's linear, right? So that's all right. Let's look at the results. First of all, I let it run for a few more epochs because it's a bit more complex to run it. In the end, it reached 98%. Let's be fair, at epoch 6, okay, it reached 98.89%. So it is better, even at the 6th epoch, than our MLP already, with 1/5 of the parameters, right? And this is because it doesn't have to learn that the 6 written here and a 6 written there are still 6. Because it can extrapolate this from the translational equivariance, that's what you call it, not invariance, but the translational equivariance of the convolutional neural networks. This is a feature you buy just by using this model. So it takes a lot less parameters to learn something better than the MLP was doing, right? Let's look at the training and at the validation. Here's. So, I was pressing this guy. Not really rising anymore, right? It reached 99%, then went back to 98.8, 98.9, and here is steadily rising though.